Welcome everybody. We have a pleasure to host today Carlos Bravo-Pietro from University of Barcelona and Technology and Innovation Institute in Abu Dhabi. Carlos is a PhD student of Jose Ignacio Latoya, and Carlos specializes in near-term algorithms, especially variational quantum algorithms, right? Okay, variational approaches to quantum computing. And today he'll be telling us about how to apply them in the context of linear algebra applications. So thanks for coming. The screen is yours, Carlos.
Okay, so thank you very much for the introduction. Yeah. So as you said, my name is Carlos Bravo-Pietro. I'm currently a PhD student at the University of Barcelona, also working at the Technology Innovation Institute. And the idea today is to present some of the works that I've been doing during my PhD that I grouped under the title of Variational Quantum Architectures for Linear Algebra Applications. In particular, I would like to present three different works. The first one is the Quantum Singular Value Decomposer to produce the singular value decomposition of bipartite pure states. Then I will jump to the Variational Quantum Linear Solver, which is a variational quantum variational quantum algorithm for solving linear systems of equation. And then I would like also to present my latest work related to quantum generative adversarial networks to learn underlying distribution functions. So right now we are living the so-called noisy intermediate scale quantum era, where current quantum computers have a low number of qubits, from 50 qubits to a few hundreds, best case scenario in the near future. With low coherence times, we can perform of the order of 1,000 operations before decoherence wipes out the result. And also we have no error correction. So yeah, basically these quantum computers are not yet capable of larger scale quantum computations. And the question is, can we do something useful with these quantum computers? And yeah, actually, probably no one really knows the answer to this question, but at least we have some promising candidates. Among them, there are the so-called variational quantum algorithms. So these algorithms, in general, do not need a high number of qubits, say, can be implemented with shallow quantum circuits and are hardware efficient in the sense that you can adapt the gates that you are implementing to the particular chip architecture, and also have been shown that they are slightly noise resilient. So probably you are really very aware of how a variational quantum algorithm works, but just to be sure that we are in the same page, the idea of these variational quantum algorithms is that you have to encode your problem into some cost function, and then you will use some classical quantum hybrid loop to minimize this cost function, which is in general encoded into some Hamiltonian. So here you can see the general sketch of a variational quantum algorithm. So here we have our quantum computer that we are going to use to prepare quantum trial states that will depend on some classical parameters. The idea is that we are going to measure this quantum trial state. We are going to do some post-processing if it's needed. We are going to compute the cost function, and we are going to deliver this cost function to a classical optimizer. And the idea is that the classical optimizer will deliver a new set of classical parameters so that you tune these gates, you propose a new quantum trial state, and so on and so forth. So you repeat this loop until you reach some stopping criteria that in general is user specified. And ideally, you would have solved the problem. So let me start with one of my first works, which is the Quantum Singular Value Decomposer. So as you can see, as you will see, this is a very basic variational quantum algorithm made of a very intuitive idea. So I think it's a good way to start. And this was done in collaboration with Diego García Martín and José Ignacio Latorre at the University of Barcelona. So imagine that you are given an unknown bipartite quantum state, and you want to study the entanglement spectrum of this bipartite quantum state. So typically what you would do is perform some measurements in different basis to retrieve some data, and then perhaps you could construct the density matrix, compute the reduced density matrix, diagonalize it, and then you could cast the state into its Smith form. No? And now by having this form, you simply, by reading these Smith coefficients, you basically have full information of the entanglement of the system. No? So what we propose here is to cast this unknown state into a Smith-like form of this one that you can see here, where now the Smith eigenvectors are the computational basis here, and you can see here that you maintain the Smith coefficient. So how we do this? We basically apply two different unitaries on each subsystem that we are going to train to perform this transformation. And basically, the figure of merit for training these two unitaries is to force exact output coincidence when we measure. So by doing this, you basically cast the state in this form here, because notice that we have no entanglement between the systems, so therefore the Smith values are basically preserved. So once you manage to train these unitaries and you have the state on this form, you basically have to measure the probability of finding the computational basis states, and by simply measuring the probability, you have the Smith coefficients. So notice two interesting things. The first one is that typically variational quantum algorithms are trained to minimize some Hamiltonian energy, typically. And in this case, this is a slightly different. No? So we train to satisfy some particular correlations between the system. Although obviously you can cast this problem as minimizing some Hamiltonian, but the original form is this one. So basically satisfying some correlations. And there, another interesting thing, perhaps compared to other techniques to compute the entanglement spectrum, is that in this case, we only measure in one setting. So we always measure in the computational basis. So we don't have to measure different observables. And yeah.
Sorry, Carlos.
Yeah.
But like, what is exactly the cost function you're looking at? Yeah.
Yeah. So the figure of merit is the number of strings that are different here. So we try to minimize the difference. So we penalize when we measure something different in both subsystems. And actually, more in detail, we penalize by the Hamming distance. So
I see. So like if you were to, let's say, encode it as a Hamiltonian, it would be probably like highly non-local Hamiltonian.
No, it would be too local.
Too local.
Yes, because you would simply read, for instance, this qubit and this one. This is a sigma C, sigma C.
Right.
Would be a sum of two local Hamiltonians.
Okay, but then you ensure that the strings, let's say, are like between the first qubit A and first qubit B, like there are just coincidences. But yes. Then
and you would add like this contribution to every qubit. So at the end, your cost function is going to be 0 if you have exact output coincidence.
Okay, whereas fine. Okay, so then it's like specific, essentially, like some specific Kubo problem in a sense. Yeah.
Yes. Yes. Where we only measure sigma C in the sigma C basis. Yeah. In some sense, yes. You can think it like that. Yeah. So as I was saying, the interesting thing is that here we can study the entanglement by simply measuring one basis instead of, for instance, performing quantum tomography, for instance, that it would require to measure in different bases and so on. And this may be exponentially hard, worst case, And this is the type of answer that we are going to use in the simulations that I'm going to show you in the next slide, where these are rotations. So the trainable parameters are inside these rotations here. This is what we're going to tune in the optimizer. So yeah, as I said, once it's trained, we can read out the entropy spectrum because we have the state in this form here. And now we're basically measuring the computational base, the probability of finding a particular computational basis state. We can read these Smith coefficients. And now, for instance, we can compute the entanglement entropy. So in this case, I'm showing you some examples for random quantum states with 6 qubits with a bipartition of 3 and 3. And as you can see, as we increase the number of layers of our ansatz, so this is one layer of our ansatz, and we can concatenate several of them. So the more layers that we have, the better approximation we have to this unitary that diagonalizes the system in some sense. So as you can see, as we increase the number of layers, we reduce the error of the computed entropy, and we are basically on the top of the line, which would mean that we have the exact entropy, the one delivered from the quantum singular value decomposer. Another interesting thing is that now we can also recover the eigenvectors by simply applying the inverse unitary to the computational basis state. So this is something we can do as well if we are interested in the eigenvectors. And also, two interesting spin-offs of the quantum singular value decomposer is that, for instance, once the circuit is trained, it can be used as an autoencoder. So notice that now, once it's trained, by simply applying control NOT gates from one system to the other, we basically compress all the information in one of the subsystems, because we have basically disentangled the two subsystems, and this is basically an autoencoder.
Sorry, Carlos, but like, what do you mean by putting all the zeros in the A register? Do you do post selection on all zeros?
No. Now, so since we had exact output coincidence, do you remember? So now by simply applying control nodes, we always are going to measure zeros here. Always. We have disentangled both subsystems. Now we have two pure states. So here you have the state.
No, I'm a bit confused because I thought that you could have, in principle, any bit string in the first register, as long as you don't have coincidences, as you have coincidences with the B, right?
So what
like here you have 0, 0, 1, for example.
So this is what a measurement, a particular measurement of the instance.
Yeah.
So if you're in this case, so if you always measure the same bit string here and here, you basically have the state in this form here.
Sure.
So this is the computational basis. So if you measure here 0, 0, 1, you always measure here 0, 0, 1. You measure 1, 1, 1. Yeah. So now.
So here.
So you are here in this situation.
Something, but like, why can you put all zeros in the first register?
Because if you here, for instance, you would have a 1 here, you would control this 1 and would be 0. You had here a 0, this would be a 0 as well, and then you would have a 0 as well. And this is what happens in all the possible combinations that you have in your quantum state.
Okay,
so you have
I
basically
also the B branch of the state has specific property, and you use
yes, exactly. Yeah. So now by simply applying control NOR gates, you always gonna measure 0 here. So you have, say, a pure state. You have disentangled both subsystems, and this is what is known as an autoencoder. You have compressed all the information here. Okay. And another interesting spin-off, I'm not sure if it's very useful, but for sure it's interesting, is that you can perform a long distance swap. So now, once you have trained the quantum singular value decomposer, you could, for instance, classically communicate the optimal parameters to Bob or Alice. They could apply the inverse unitary with your parameters, and you would see that this is basically, you have performed a swap operation. And obviously, the quantum swap operation is better, but in this case, you could do it at a long distance, which is the interesting thing. So if there are no questions, let me jump to the second algorithm, which is the variational.
So maybe can I ask, like, what is the sample like? Can you say something about sample complexity and depth of the circuits that you have to?
Yeah. So as you know, doing complexity analysis in variational quantum algorithms is very difficult. But in this case, problems could be the first one, that the needed circuit to implement these unitaries may be exponentially large in the size of the system. This is something that may happen. Another thing that may happen is if the state that you are measuring has a lot of entanglement, you would have an exponential number of Smith coefficients, and therefore you would need an exponential number of measures to read them. But I mean, this of course makes sense, no? Because if you want to have an exponential amount of information, then you would need an exponential amount of measures. This is something that you can escape. Regarding these particular simulations, so this simulation for 6 qubits, the order of optimizations steps that we need was of few hundreds, 200 optimizations, something like that. This perhaps could scale well for some particular instances, but this also could scale very bad depending on the quantum state. But yeah.
And what input state? How you generated your input state?
These are random states. We basically take random values between minus 0.5 and 0.5, and with complex. So the random state would be putting random values between minus 0.5 and 0.5 plus the same randomization in the complex regime, and then
sure. Okay, so this is kind of for let's say for numerical experiments.
This is purely
I dare to say that for such states, probably you'd like for purely random states, you'd like probably need exponentially deep.
I would say so. Yes, same. So the idea of this is, for instance, to use it for I don't know, condensed matter systems or this kind of things that perhaps the unitaries that you need do not scale exponentially, and also the entanglement is not that large.
Related question: when you talk about 200 iterations, is it just the iterations of the minimizer, or
yes,
how many kind of measurements do you have to perform to get sufficient statistics?
Yes, so this is the number of iterations that the optimizer does, but on each iteration you would need to compute. You would have to measure several times on the quantum computer, so you would have to run several times the quantum computer. In these particular simulations, we do a state vector simulation. So we assume that we have full description of the quantum state. So we don't perform measurements.
No, but when you do the numerical simulation, kind of you can read off the coefficients to whatever position you do in the simulation. But when you run it on a real computer, to me, kind of the question is, at the end of the day, wouldn't it be as efficient to do full state tomography? To get the same position of the result.
Yes, this you would have to compare the number of measurements that you need for full quantum tomography to the number of measurements that you would need for optimizing the unitaries. Yes.
And you didn't do that yet?
No, we didn't. So, I mean, for this 6 qubit state, you would need to perform 3 to the power of 6. Well, you would have to compute 3 to the power of 6 observables, right? The expectation, so all the possible combinations, all the possible, right? The correlators. And in our case, we did a few hundred iterations. I believe is more or less of the same order in this case, that doing full quantum tomography. Yeah.
Thanks.
But I guess this will depend on the particular, as we were saying, this is the case of random quantum states, and probably the size of the unitary is exponentially large in this case, and perhaps this case you would need more optimization steps because your unitary is larger and you have more classical parameters. But in practice, who knows? No?
So just a follow-up question, just to be, let's say, I mean, okay, let's say I understand that probably in the worst case you would need exponentially deep circuits to do it, but let's say on the let's say forget about circuits for the second. Let's just you have this cost function kind of behind the scenes, right? So do you? But if I understood well, this is just some specific to local Hamiltonian. So the number of samples that you need to kind of efficiently estimate it wouldn't scale exponentially with the number of qubits, or it will.
It will depend on the entanglement of the unknown quantum state. So if the entanglement is very, very large, then you would have here an exponential number of possibilities, say, when measuring. So you would have all the possible combinations.
That is correct, but in the end, you are evaluating just energy of a local Hamiltonian, right?
Mm-hmm.
If I understand well.
Yes, that's true. So you would, yeah, obviously the error would depend on the number of measures that you do at the end, no? Mm-hmm. So you are saying how this error depends on the quantum state, or in particular, or I don't know.
No, I meant how it depends on the number of queries to your circuit. But I guess it's this part probably is not prohibitive, right?
So how the errors will depend to the queries, no? Well, I guess as in any variational quantum algorithm, no, you would have the uncertainty decreasing with the square root, no, of the number of samples that you that you perform.
Yeah, I guess we are on the same page. Just I guess this cost function, you wouldn't need to, let's say, sample the state exponentially many times. Just
not necessarily. No. You would have some error that would depend with the number of samples that you have performed, no? And this would decrease with, well, this is something I would have to compute, but very likely with the 1 over t square root, no, something like that, the number of samples. Yeah. Okay. So if there are no more questions, I'll jump to the second part, which is, I was saying, is the Variational Quantum Linear Solver, which is a variational quantum algorithm to solve linear systems of equations. And this was done in collaboration with Ryan LaRose, Marco Cerezo, Jiki Tsubasi, Lucas Cincio, and Patrick Coates. So this is the notation that I'm going to use in the following slides. So we are given A and B, where, so as I was saying, this is the notation that I'm going to use in the following slides, where A is an n by n matrix, B is an n-dimensional vector, and we want to solve for x. And we are going to assume that the norm of A is less than 1 or equal to 1, and that the condition number of this matrix is under control. So this means that basically the condition number is less than infinite. So linear systems of equations appear in multiple fields and are very useful for machine learning, for instance, partial differential equations, or even analyzing electrical circuits, if that's your thing. So the hope, so classical algorithms scale, best classical algorithms scale polynomially with the size of this matrix A. And the hope is that quantum algorithms will provide an exponential spiral. And sure they do, no? So I think we are all familiar with the HHL algorithm from Harrow, Hasidim, and Lloyd. So the idea of this quantum algorithm is to prepare the quantum state X, which is proportional to the classical solution. Here, this quantum algorithm scales logarithmically with the size of the matrix under certain constraints. And also recently, we've seen some further improvements that reduce the complexity in the condition number and also in the error epsilon. But the problem here is that this quantum algorithm requires deep quantum circuits. And that's why we proposed this variational quantum linear solver, which is basically more geared towards NISQ devices. So what do we need?
Just can I comment? Okay, yeah. This is the comment that people typically say in this context, but just this is a beautiful algorithm, but the solution is in the form that it gives. You don't get coefficients, you don't get entries of this of this vector. You just have a state that encodes it, and you need to measure it, and it might be still take a lot of time to measure it, right?
Yeah. So actually, what you obtain at the end is the quantum state, which is proportional to the classical solution. But indeed, you cannot read the full vector because otherwise you would lose the exponential spiral. So at the end, you are interested in computing some observables with this quantum state and so on. But yeah, indeed, you will not measure the whole quantum state. because you will lose the exponential spiral in that case.
Sure.
Yeah. So so what do we need to build this variational quantum algorithm? So first, we will have to define a cost function, and it better be faithful in the sense that when this cost function has a value of 0, then this would mean that you have solved the linear system. Then ideally, we would like to give some operational meaning to this cost function. And as we will see, this is basically relating the value of the cost function to some of the properties of the linear system. And this would mean that we will have some solution guarantees, but this is something I will explain in the following slides. And ideally, also, we would like to have or to find a circuit that computes this cost function, which is efficient quantumly and is hard to compute classically. So this is the full sketch of the quantum algorithm. As in any other variational quantum algorithm, we have the input part, the classical optimization, and then the output of the algorithm. But let me go step by step in each of them. So indeed, in the input, we will have to specify the linear problem. So we will have to give the matrix A and the quantum state B. As in, for instance, the HHL algorithm, we are going to assume that the quantum state B can be produced by simply acting with an efficient circuit U on the 0 state. This is a common assumption. What is not so common, and you may not like it, but it is what it is, especially if we are trying to implement it on niche devices, is that we assume that A is going to be given by a linear combination of unitaries of this form here, where A, the norm of A is going to be less than 1 or equal to 1, as I said, and the condition number is under control, so less than infinite. So this basically means that the linear system has a unique solution, basically. So in the optimization part, basically the goal is to prepare the quantum state, which is the solution X, such that when acting with A, we have a quantum state proportional to B. And we are going to do this by using a variational quantum circuit. Again, this is in particular, this is the circuit that we are going to use for the simulations that I'm going to show you, where again, the classical parameters are going to be inside this rotation. So this is very typical in variational quantum algorithms. What is not so typical is this, that I will enter in more detail in the next slide. But the idea is that in this variational quantum algorithm, by simply reading the value of the cost function, we are going to know how close we are to the exact solution of the linear system. So this is actually very interesting, because now we can set some particular error, epsilon, and we can use this relation between the error and the cost function to set some stopping criteria for the variational quantum algorithm. So once the cost function has reached a particular value, we are sure that we have less than this particular error, and we can stop the variational quantum algorithm. And finally, the output is simply, once we have reached this stopping criteria, we have the optimal parameters, and now we simply input these classical parameters, optimal classical parameters, into the variational quantum circuit, and we can basically we have the solution of the linear system, get X. And now we could compute, as we were saying. Now the idea is that you can compute observables or whatever, but the idea is that you don't measure the whole quantum state, because you would lose any potential spiral. So let me specify or talk about the cost functions, because as I was saying, cost functions are very, very important in variational quantum algorithms. In particular, in the paper, we propose 4 different cost functions, but here I will show you 2 of them. The first one is the so-called, what we have called global cost function, which is this one here. We have called this the global cost function because, as you can see, this is basically constructed with global operators, and so you see that this is very intuitive. So what we basically do is we simply try to minimize the orthogonality between A acting on X and B, basically. So we are trying to minimize this orthogonality. So as I was saying, this cost function is very intuitive, but as we will see in the next slide, this cost function leads to barren plateaus. and this is a problem when training variational quantum algorithms. So we decided to propose a different cost function that we have called a local cost function, which now basically is equivalent, but now this orthogonality test is done locally, qubit by qubit. Another interesting thing is that one can prove these inequalities here, which basically means that if one of them is 0, then the other one is 0, and this basically means that we have solved the linear system. So both cost functions are faithful.
Sorry, can I ask?
Yeah.
So this is, yeah, this is for like you have this nice equivalence for values of cost function equal to 0. But what if it's just smaller than epsilon, this value? So like, do you get some fidelity? Can you get some fidelity estimates from it?
No, given a value of the cost function, we can be sure that the error, the maximum, so we have an upper bound of the error with the fidelity side. This is something I will show you.
So it works as some kind of fidelity witness for the
yes. Something like that. Yeah, I will show you in a couple of slides this relation between the cost function and the error. So let me first. I'm not going to show you now results. Simply let me address the Br-Pietro issue between the global cost function and local cost function. So we try to solve some family of linear systems, okay, with some particular condition number. And here I'm showing you the value of the cost function as we keep doing iterations in our variational algorithm. So in blue, you can see the values of the local cost function, and in red, you can see the values of the global cost function. And as you can see, the local cost function, so this is for different number of qubits, and you can see that the local cost function, it can be trained even up to 50 qubits. Whereas in the case of the global cost function, when we reach the value of 50 qubits, basically we see a Br-Pietro. So the gradients are basically 0, and we cannot train it. So this is why I mentioned that defining a good cost function is very important for variational quantum algorithms. And in particular, if you can define the cost function locally, even better. So let me enter into the.
Sorry, I'm a bit. Can you move back a bit? So
yeah.
Right. So there is this behavior. I mean, I just wonder to what extent it's fair to compare sort of unconditionally values of those functions, because like in the previous slide you were showing that actually this local can be much larger by a factor of n, right? So how right, so isn't it what you're showing just artifact of this inequality, like, you know?
No, because, well, you can I think I understand. Yes. Okay. So I mean, you can clearly see that you have a plateau here. So the gradients are basically 0. So you cannot train it. Yeah.
Okay.
Yeah. Okay. So let me address this operational meaning thing that I was mentioning earlier. So one can show that you can relate both cost functions with the epsilon error and the condition number of the linear system, where epsilon is defined like this as the trace distance between the exact solution of the linear system and the solution proposed by the variational quantum linear solver. So by simply looking to this inequality, or this one in particular, now one can relate the error with the condition number, the number of qubits, and the value of the cost function. And now you can clearly see that by simply reading the value of the cost function, we have an upper bound of the error that we are dealing. So you can basically specify a particular error, and you know that your cost function has to reach a minimum value so that you have that particular error. And this can be used as a stopping criteria. So let me show you some examples, some simulations. So first, we try to simulate an Ising type linear system of this form here, where we basically tuned these parameters so that we can control the condition number of the matrix A. So these are some of the results. So here I'm showing you what we have called the time to solution versus the condition number of the matrix of the linear system and 1 over the epsilon, where basically the time, you can see the time to solution as something proportional to the number of iterations to guarantee some precision epsilon. So here we are not doing any cheating. We don't know the exact value of the precision, but we use the upper bound of it. So we don't know the exact precision. We simply use the upper bound. And as you can see, this heuristic scaling shows that for this particular example, this is in like linear systems. The scaling is slightly sublinear in the condition number and also logarithmic in 1 over epsilon, which is great. Also now, if I show you this particular scaling, but with a number of qubits, you can clearly see that it scales linearly with the number of qubits, which would mean logarithmic in the dimension of the matrix A, which would mean over a naive method would mean an exponential speed up, but indeed this is for this particular case, which is might be a trivial example, which is this.
Sorry, this because I got distracted for a second. So this is a free. Is it like a free fermion Hamiltonian effectively?
Nising-like Hamilton matrix A linear system.
So this A. So
A is
so
the
yeah. So probably yeah. So it's exactly solvable, I guess. This one, right?
Very likely, yeah, exactly. So that's precisely why we went to a harder example. So now instead of considering this is in like linear system, we decided to implement a random linear system, or at least we try to randomize the linear system as much as possible. Again, we tune these parameters so that the matrix A has some particular condition number. And here we are basically this P here. So we are trying to switch on and off different two-body Pauli operators that we choose randomly as well. And then we also give randomly some coefficient between -1 and 1. So we try to randomize as much as possible this linear system so that this is a harder example. So again, I'm showing you here the time to solution versus the condition number of the linear system and 1 over epsilon. And as you can see, again, the scaling appears to be slightly sublinear in the condition number for this particular example. Again, logarithmic, one with 1 over epsilon, which is great. And if we move on to the how this scales with the number of qubits, you can see that this time the scaling, instead of being logarithmic with the size of the matrix, is basically polylogarithmic with the size of the matrix with a factor 1.5.
Well, can I just comment? I mean, sorry, like you just went through from 2 to, I know this is number of qubits, so with the size of the matrix. Yes. So sorry, well, how you measure this? So the n is the logarithm of the dimension now.
The n is the logarithm of the of the dimension.
Okay,
so we have a
okay.
It's still an exponential speed up, but in this case the scaling is polylogarithmic with the number with the size of the matrix instead of logarithmic. So this, I mean, some sense are great news. And now finally, let me show you one example that we implemented on Righetti's quantum computer. This was done a few years ago. Again, we used this Ising type linear system, where again we tuned these parameters to have a particular condition number, which in this case was pretty low, to be honest. So here are the results of the cost function evolution as we train the algorithm. The black line is the quantum simulator, and the red and green line are 2 different runs in the quantum chip. And as you can see, we obtained pretty small values of the cost function, but indeed not as low as the quantum simulation, because now we have noise and decoherence. By the way, the linear system that we implemented is with 10 qubits, which is a linear system of 1000 by 1000 the dimension of the metric is 1000 by 1000, which is, I believe, the largest implementation on real hardware or trying to solve a linear system. And also, something interesting that we observe is that although the cost function values are not as low as the value coming from the quantum simulator, also the quantum simulator, we obtain the correct optimal parameters. So the parameters were equivalent. And this is actually nice because we could, for instance, if we obtain the correct parameters, we could, for instance, now apply some error mitigation techniques, for instance, and compute with more accuracy observables that we are interested in. So if there are no questions, I would like to move to the last paper that I wanted to show you, which is the style-based quantum generative adversarial networks for Monte Carlo events in collaboration with Julien Baglio, Marco Se, Anthony Francis, Dorota Grabowska, and Stefano Carrazza. And as you will see, we focused on high-energy physics. However, this style-based quantum generative adversarial network can be used to any Monte Carlo event generation. So as I was saying, we focused on high-energy physics, but I mean, I don't have background in high-energy physics, but I can certainly say that the LHC produces like millions and millions of proton collisions per second, and this is a huge complex environment. No? So the problem is that the simulation of these events are very intensive and requires lots of computing power. So very, very recently, many people try to approach this event generation, but using classical machine learning techniques, where the idea is basically to train with a small data set and then use machine learning networks to learn the underlying distribution of some physical processes, and then generate for free a much larger data set. So this is actually what we do, but using quantum generative adversarial networks. But first, let me explain very briefly what is the generative adversarial framework. I'm not sure if you are very familiar. So, 1 second. The idea here is that you have two competing networks, the so-called generator and the discriminator. They will compete. So the generator will try to create or to produce fake data. And the goal of the discriminator is going to be to distinguish between real data and fake data coming from the generator. So this is the training that we are going to follow, where at the end, we're going to have an adversarial game where the generator will try to map some input noise distribution that we are going to fit in the generator to the underlying reference distribution. This is the real one that we are giving to the classical discriminator. The discriminator will try to distinguish between the real data and the data coming from the generator. So let me do this R4 analogy.
Sorry, I'm not so familiar with this with those concepts. So this classical discriminator, is it fixed? Are criteria used there fixed? Let's say.
No. So you have two different networks, and none of them is fixed. You are going to train them. You are going to train the discriminator to distinguish between real data and the data coming from the generator, and you are going to train the generator to fool the discriminator. So both of them start from scratch, and they will play an adversarial game to learn. On the one hand, the discriminator will try to learn how to distinguish data, real data and fake data, and the generator will try to learn how to create fake data to fool the discriminator.
Okay, but then what's the point of this game? In a sense, like I imagine, I just naively I imagine that if criteria, so that is to say, discriminator is fixed, then it makes sense to train some network to fool this guy, right? Like on the other hand, like so, is it? On the other hand, if we knew how we are gonna, let's say, fake data, it makes sense to optimize the discrimination. But I can imagine each of those scenarios separately, right? Like that they can come from some application. But this intertwined optimization or this game, like
So
when
this is
it can occur, like in practice, like what is the problem, like when,
so the goal is at the end to have, so in our case, the goal is to have a generator that learns the underlying distribution of the real data. So at the end, after you have trained both the discriminator and the generator, ideally the generator will understand the underlying distribution that we have trained it with, which is this one that we are going to deliver to the discriminator.
All right. So because you optimize also the classical discriminator, you sort of okay, you sort of like this generator, let's say, learns, like recovers as like many features of the underlying distribution of the truth.
That's it.
That's
yes.
the idea. Okay.
So the generator, learns the underlying distribution because of the information given by the classical discriminator.
Okay, thank you. Sorry, I'm not that much.
Yeah, so perhaps with this analogy, I think might be easier to understand. So you can imagine that the generator is an art forger and the discriminator is a art historian. So the goal of the generator is to create fake paintings that look authentic, and the art historian will check these paintings and will try to catch the forgery. And basically, the training is going to be a catch me if you can game between the art forger and the art historian, where the success is basically when the generator, so the art forger, will create forgeries that are so good that the art historian has at most 50% guess ratio. So will only guess randomly. And this would mean basically that the art forger, creates new work that look like the authentic one. So to be more precise with the training procedure, as I mentioned, the training is basically we are gonna train alternatively the generator and the discriminator, where these parameters here are the trainable parameters. This is the noise input distribution that we are gonna deliver to the generator. So the generator at the end learns to map this noise distribution to the fake data that look like the authentic. And here is we input here the data to the discriminator so that it can decide whether it's real or fake. So the mathematical tool that we are going to use is the binary cross entropy. And we are going to have two different loss functions, as I mentioned. So we are going to train the generator and discriminator. The loss function of the generator is basically the probability of the discriminator classifying the data coming from the generator as fake. And this is something that we want to minimize. So we want to minimize the chances of the discriminator saying that the data coming from the generator is fake, right? On the other hand, you can see the loss function of the discriminator as, on the one hand, the probability of the discriminator saying that the real data is real, and saying that the data coming from the generator is fake. So this whole thing is something that we want to maximize for the discriminator. So the goal thing is that this is a min-max two-player game, and it has been seen that when you have the optimal parameters for both the discriminator and the generator, you reach a Nash equilibrium between both loss functions. So both loss functions will have the same value. Okay. So moving on. What time is it now? Yeah, perhaps let me skip this one. So so what I mentioned is applied to the classical case, no, where you have a classical generator and a classical discriminator. But in the particular setup that we have used for this paper, we only used a quantum generator. So we use a quantum generator to create the fake data, but the discriminator remains classical. So let me, before going to the results, specify a bit about the quantum generator. So again, the quantum generator is a variational quantum circuit with some rotations and some entangling gates. But here we have the novelty of our work. So as I was saying, you have to always input a noise distribution into the generator, and this was typically introduced at the beginning of the quantum generator. So in the first layers, people would typically introduce this noise distribution. Whereas in this case, we insert this noise on every gate of the quantum circuit, and not only in the initial quantum state. And we introduce this noise simply as a linear interpolation inside the rotations. So these two things are the trainable parameters, and this thing here is the noise distribution. That we are going to multiply it by some trainable parameters at the end. The whole rotation will depend on this noise input distribution. And also recall that the final goal of the quantum generator is to create fake data. So in particular, this is how we generate the fake data. So if we have a, say, a 3D distribution, we will need a vector with 3 components, and each component is going to be delivered by one of the qubits. And in particular, is going to be the expectation value of the sigma C operator. So each qubit will deliver one component of the fake sample. So if we have a 3D, say 3D probability distribution, then we are going to use 3 qubits, for instance. So let me go to the results. So first, I would like to show you simple results for the 1D gamma distribution. So this is a very simple case, a validation example. So since this is a 1D distribution, we only need 1 qubit. We only use 1 layer, so the circuit is very shallow. And we use 100 beams to discretize the distribution. So we are going to train the quantum generator with, so the whole framework with 10,000 samples. So so you remember that we have the classical discriminator, the quantum generator, and for training the classical discriminator, we are going to show fake data and real data. The real data that we are going to show consists of 10,000 samples. But then we are going to use, once it's trained, we are going to use the generator to generate 10,000 samples. And also we are going to ask for 100,000 samples. To demonstrate that the quantum generator can be used in data augmentation context. So we train with 10,000 samples, and then we ask 100,000 samples. So we ask for more samples. So here I'm showing you the values of the loss functions. So this is how a well-trained quantum network, the quantum generative adversarial network should be. So this is how it should be seen. So first we have a warm-up phase where both cost functions oscillate, and then at the end we reach this Nash equilibrium that I was mentioning before, where both cost functions have the same value. I'm not sure if I should finish soon. I guess so, no? Because we are. I'm about to finish.
Technically 5 minutes.
Okay,
but I think don't like if you if you want to speak for 5. That's also fine.
I think should be fine. So once trained, these are the results. So now I'm showing you here the density of samples for the reference distribution, so the real distribution, and the distribution generated by the quantum generator. For the case of 10,000 samples, and for the data augmentation case with 100,000 samples. And as you can see, in both cases, the KL divergence is actually pretty small, and therefore the quantum generator with a single qubit and 1 layer can learn the underlying 1D gamma distribution, which is great. So let me move to the real example. So here I'm going to show you some results for the proton-proton collision to T bar. Again, we are going to train with 10,000 samples. And we are going to train with the so-called Mandelstam variables, which are the ST and the rapidity Y of the proton-proton collision. So we are going to have a 3D dimensional distribution. Again, since we have a 3D distribution, we are going to use 3 qubits and only 2 layers. So the circuit is very, very shallow. And these are the results for the 1D marginal distribution for the S, T, and Y distributions. And again, the reference distribution is the red one, and the generated distribution by the quantum circuit is the blue one. And again, you can clearly see that we match pretty well the reference distribution with pretty small KL divergences. So the results are somehow successful, especially if we consider, we take into account that we have only used 2 layers, so a very shallow circuit. The cool thing is that now, since we have a 3D distribution, we can also plot the 2D projections, so to see the correlations. As you can see, the correlations are very well captured, which is also quite nice. And recall that we are in the data augmentation context again. And especially now, if we look into more detail and we plot the ratio between the reference and the generated, we can see more detail that in the central parts of the distribution, we have these white colors here, which would mean that we have perfect ratio. And then in the tails of the distribution, we have not so good results. But this is very typical in generative adversarial networks, also in classical generative adversarial networks. So, okay, the KL divergences are pretty small, even in the case of that augmentation, but are these results maintained on real quantum hardware? So we decided to deploy our model into IBM quantum hardware, particularly IBM Santiago, which is a 5-qubit machine with this particular architecture. And these are the results of the distributions. Obviously, the results are not so good as previously. We have some weird peaks in the distributions, but basically this is due noise and decoherence, but still we managed to have somehow a small KL divergence, which is cool. And also now if we plot the 2D projections, we can see that the correlations are maintained. So we have not destroyed the correlations with the noise and the decoherence of the machine, which is actually quite nice as well. And the results for the ratios, obviously not as perfect as previously, but still decent in some sense. And finally, before finish, let me show you also some examples that we obtained running on IonQ quantum hardware. So we deployed our model onto IonQ machines, not to compare both architectures, but to simply assess whether this quantum generative model is in some sense hardware independent, no? Because now we have different errors between different fidelities in the quantum gates, different decoherence times, and so on, and different connectivity. The problem is that we had actually access constraints to IonQ, and the test was limited to only 1,000 samples. But at least we can compare with these 1,000 samples, and as you can see, the results were somehow very similar between both architectures, and we can say that the implementation is in some sense largely hardware independent, which is nice. And yeah, with this I'm done. So thank you very much for your attention. If you have any questions, I'll be happy to answer them.
Thank you, Carlos, for a very nice talk. Yeah, we have time for questions, comments to the speaker. Yannick, you want to? Oh, okay.
Yeah, I wanted to ask, but well, go ahead.
Please.
Okay, so maybe I would have a question regarding the algorithm to find the SVT decomposition of, the Schmidt decomposition of a state.
Yeah.
So, like finding this decomposition is like finding the eigendecomposition of the density matrix, which is which describes one of the subsystems. So have people thought, okay, this is a naive question, so I don't know much about this stuff. So have people thought of like finding the eigenvalues after application of some positive maps, like partial transposition?
Can you repeat, please, the question? The eigenvalues
of a density matrix after application of, let's say, partial transposition?
I don't think so, or at least I'm not familiar with anything similar. No. So I don't think so.
Okay.
No.
Thank you.
Other questions or comments? Marcus, did you want to ask something? I didn't notice.
I would like to return to the question of linear solvers concerning this cost function. I understand that the cost function is essentially proportional or gives an upper bound on the position. So I would expect that you have to determine the cost function to the same position you want to have the solution in the end. But then you state that you had kind of polylogarithmic complexity in the position. Which is to me contradicting in terms of sample complexity.
Yeah, so again, these simulations, indeed, we would have to include the sample complexity. So these simulations were performed with a state vector. So we assume that we have exact precision of the amplitudes and therefore exact precision of the observables. So in this, you would have to, if you want a more realistic approximation, you would need to perform measurements, and this, indeed, may imply that.
I have the impression that your cost function would essentially be linear in the position. And so to get an estimate of the cost function, you have to have the same position as you want to have the solution. And that would spoil your exponential advantage in terms of sample complexity.
Indeed, it depends on the error, no? In this case, I'm not sure if we'll spoil the advantage. So again, the precision will scale with 1 over the square root of the number of samples. And perhaps, I mean, it depends on the error, no? At the end, the value of the error. If you want to have a very small value of the error, then you would need to perhaps perform a lot of.
You pointed out that the scaling in the position was polylogarithmic, if I remember correctly.
Yes, because here we are not performing measurements. So we are performing a state vector simulation. And indeed, perhaps you are right. If once you include the measurements, you perhaps lose this logarithmic scaling. This is something I would have to think.
And kind of related, since your quantum circuit essentially gives you a description of the solution. The solution is a vector in capital N-dimensional space. So I would expect, if you don't make additional assumptions, that the number of parameters you have to have in your circuit would also scale with the dimension.
It depends on the, I mean, it depends on the quantum state in particular. Indeed, if you have a random quantum state, you would need an exponential number of classical parameters. But the same would happen in the HHL. Then you wouldn't be able to reach the quantum state efficiently, the solution.
No, there the assumption is that you have a sparse matrix or that you have an efficient description of the matrix.
Yeah, in this case, the only assumption on the matrix.
Here, if you had an efficient description of your solution space, then I would expect that you could also use that information for any classical algorithm.
Yes. So in this case, the only assumption is that it has to be given as a linear combination. But indeed, it may happen, no? As you mentioned, that the description of the quantum state has to be.
I understood that you are learning a quantum circuit that produces the solution.
Yes.
Kind of from a fixed state. So that is an implicit description of your solution via a quantum circuit.
Yes, this is a guess. You simply.
And so if you don't know the structure of your solution a priori, kind of you cannot restrict your quantum circuit.
Yes, indeed.
The number of parameters in the quantum circuit is that without additional assumptions has to be at least the same as the number of parameters you have in the solution space.
This is in the worst case scenario, no? I would say. So not always. You may have you may have a quantum state with n qubits that you can prepare with a polynomial number of classical parameters. No?
I agree, but if your solution could be found with a quantum circuit with a few parameters, then you could also use that information for any classical algorithm.
I'm not sure about that. I don't think so, no, because in the HHL algorithm, you will also prepare the quantum state with a polynomial number of gates, and this wouldn't mean that you have, or you may have, a classical algorithm that solves the problem efficiently, no? So in the HHL algorithm, for instance,
kind of, I agree that it does not necessarily imply, but
it may happen, yeah, for sure, it may happen, yeah.
So
Michael,
I'm sorry to be so skeptical, but
so can I just comment?
I understand your
this
point.
Is like what people do in this like NISQ business. You can maybe treat it as like a variational principle rather than really looking for the solution to your problem. You, let's say, use this scheme that Carlos and others propose as, let's say, variational ansatz for candidates for states, right? Just like people try to do with quantum chemistry. I mean, it has limitations, of course.
Indeed, yeah. You try to explore the manifold of quantum states as much as possible with your ansatz. And yeah, sometimes your solution may be efficiently computed with perhaps a classical algorithm, sometimes not, no? I mean, this is something that, this is why these are heuristic algorithms.
So, but okay, I have one question actually about this part of the of your talk. So actually about the cost function, because your cost function somehow implicitly depended on this matrix A that you are trying to invert, and probably the composition of this matrix as a linear combination of unitaries. So like, how hard is it to actually implement this cost function? How do I imagine that it's not, I mean, you cannot diagonalize it, and then you probably have to probe it, like it's like, is it local, like, you know?
At the end depends on the, basically on the different unitaries that you have here, and the complexity will entirely depend on this thing. So for instance, if you can express these unitaries as in the Pauli basis, you would be able to compute this very easily. If you cannot express this in the Pauli basis, you perhaps would have to implement this as a quantum circuit and perform some kind of Hadamard test, for instance, or something like that. And yes, this may be hard. It depends on the, at the end, it depends on the on this A small l. Yeah. In general, this may be hard. Depends.
Yeah, and this is why you need this. So on the implementation side, this is where you need those A's to be like unitaries, like to pull on the implementation, actually.
That's it, to implement it on the quantum circuit and compute the value of the cost function.
Yeah. Okay.
Yes.
Okay, thanks. Okay, are there any more questions to Carlos? Okay, I have maybe one last question about the last part. So yeah, also on the skeptical side, like what is the advantage of using kind of qubits there as opposed to like general, I don't know, shallow or deeper neural networks?
So that's basically the slide that I skipped. So the idea, I mean, I like to see these kind of papers as say a first step towards trying to answer like major questions, and this is, for instance, the one that you mentioned. No, so the idea would be ideally to understand whether, for instance, with a quantum gun, we can sample efficiently some distributions that with a deep classical neural network we cannot. No, and also other interesting questions, for instance, would be for a QGAN would have less parameters than a classical neural network to represent the same distribution, for instance, or would the energy consumption be reduced using a quantum circuit instead of a deep neural network. But yeah, so I think these are the main three milestones in some sense. But yeah, to be honest, I believe it's unknown whether we could be able to sample from a Q-GAN some distributions that a classical GAN wouldn't.
What about putting, because like the question is maybe what is like this, I mean, you can imagine, I don't know, using those GANs on the top of some quantum, I don't know, quantum supremacy proposal.
Yeah, for instance, yeah. For instance, if the final distribution is the Porter-Thomas distribution coming from the
sure.
Then
I mean,
we know that
no, there are some structured distributions made, like, you know, boson sampling or okay, or fermion sampling. Some people like your fermion sampling.
Yeah,
you know.
that's true. Yeah, I know.
Okay. Yeah. Thanks. Okay, you're sure. So these are like proof of principle experiments.
Yes, basically.
Okay, cool. Last chance to ask something to Carlos before we conclude. Okay. If there are no further questions, let us thank the speaker again for his time and nice presentation. Thanks, Carlos.
Thank you.
Yeah, hopefully one day we can meet in person.
Hopefully, yeah, would be great.